Okay, calculus, we're starting chapter 13. The first two sections will go pretty quick. This first one has almost no math at all. It's just talking about functions and multiple variables. The definition of a function in two variables. Let D be a set of ordered pairs of real numbers. If for each ordered pair in D there corresponds a unique real number output, then f is a function of x and y. Set D is the domain of f, and the corresponding set of values for f of x, y is the range. So for the function z equals f of x, y, x and y are independent, both independent variables, and z is dependent. So it's not really that different from a variable in two equations, or of function in two variables, just x and y. You just have a third one in here. So find the domain. F of x, y equals the square root of x squared plus y squared minus 9 over x. Our rules still hold. X can't be equal to 0 because we can't divide by 0. And we know whatever's under the square root has to be bigger than, or non-negative, which means x squared plus y squared has to be greater than or equal to 9. This is a circle. So we have to be outside a circle of radius 3. And x can't be 0. It's our domain. Those are our two requirements here. Now, let's look at b. F of x, y, z, this is now a function in three variables, is x over the square root of 9 minus x squared minus y squared minus z squared. That is the same as 9 minus x for the domain, y squared minus z squared, is greater than or equal to 0. Which means x squared minus y squared minus z squared is really less than or equal to 9. So what is this thing? It's plus, I don't know. This is it's kind of like an ellipsoid of sorts. Kind of like a football shape. But the point is, our restriction is all of those numbers added together have to be less than or equal to 9. It's kind of like it could be looked at as like a half sphere of some kind. I don't know. The shape is largely unimportant. Okay, so some rules about multivariable functions. Some are difference holds, product holds, quotient holds, so all the basic rules, and composition holds. So all the same things that happened for previous things still happen here. Now, the graph of a function in two variables is a set of all points, a set of x, y, and z, which means it's three-dimensional. The graph can be interpreted geometrically as a surface in space. To the right, for example, this is a potential function. So you might be wondering what that function is. I'm not for sure, but it's not bad to do. Okay, so let's consider the function f of xy equals the square root of 16 minus 4x squared minus y squared. Find the domain and range and describe the graph. Okay, so domain. We know 16 minus 4x squared minus y squared is greater than or equal to 0, which means 4x squared plus y squared is greater than or equal to, less than or equal to 16. Now you can look at this as x squared plus y squared over 4 is less than or equal to 4. Or if you want to go full ellipse form, x squared over 4 plus y squared over 16 is less than or equal to 1. That's an ellipse that goes out 4 in the y direction and 2 in the x direction. It has to be inside that for x and y. What do we know about z? Well, we know z is equal to the square root of 16 minus 4x squared minus y squared. Now, we know that the smallest this can be is 0, because the square root of anything is 0. The biggest this can be is 4, because if x and y are 0, this is just the square root of 16. Anything else subtracts off of it. So my range is just from 0 to 4. Now, that's literally all the math from 13.1. The other 2 pages are some interesting tidbits. There's another way to visualize functions of 2 variables using scalar fields. This is like topological maps, often like level curves, level maps, to see like it demonstrates where the height of the terrain changes, so you can put it in a 2D map. The concept of a level curve can be extended by a dimension to define a level surface. If f is a function of 3 variables, then you can create a level surface, which is kind of shown here to the right, but it's also a little bit hard to imagine what that actually looks like. But if you use technology and graph some functions, it is kind of interesting. If you take the equation, for example, c equals 4x squared plus y squared plus c squared, it creates a bunch of ellipsoids depending on the different values of c. It's basically like a Russian doll of ellipsoids, one inside the other, depending on the radius c. Of course, c equals 0, then you have no radius, it's just a dot. There's a picture of c equals 4 and c equals 16 as well. In addition to those, when you use computers to graph things, some interesting things happen. Take the equation f of xy equals x squared plus y squared times e to the 1 minus x squared minus y squared. By restricting x and y between -3 and 3, and z is restricted from 0 to 3, you can generate things like the thing to the right using traces. So traces are where it plugs in values. It's like almost like a Riemann sum where they take a few values at a time, and it creates this crater shape. Now there are some other shapes as well, and notice each of these is all the same shape, but what happens is they're different viewpoints. Like this is a viewpoint with x and y rotated for the same function. Here what we've got is a single trace, a double trace, that's in one direction and another. This one's a level curve. That's the visualization of different heights. And the last one is more of the same. And that wraps up 13.1.